And the good news is that Titan is there. The bad news is that we barely saw it. We were counting on, first of all, twice as much data because at the high telemetry rate. Secondly, we were counting on no data dropouts. So we have a good deal less data, and we're counting on lots of data in order to average it and beat down the noise. And I'd say we've said the temperature of Titan is 75 degrees Kelvin, plus or minus 5, which is about the temperature you'd expect for an object in equilibrium with the sun at that place in the solar system. And as you can see, there's no prayer of measuring a day-night temperature difference with these data. We are not looking at the surface. We are looking at the cloud tops or some point high in the atmosphere, and we cannot say what the temperature of the surface is.
Do I gather that based on the data that you did get back with Titan, there is not insufficient temperature data with respect to the surface to ascertain whether indeed there is an atmosphere that could be hospitable to some life form?
I think there's plenty of other data, Earth-based data, that tend to rule out the possibility of high surface temperatures and therefore rule out life. But I'll leave the door open a crack. And I will certainly agree with you, my data do not have much to say about the surface temperature. So perhaps summary of Saturn, or rings first. I guess I've summarized the significance of the Titan data for you already. I think we can say that our eclipse data, just as we go behind the planet, just at the end on the right there, are consistent with other analyses that imply that the rings are centimeter sized.
And the preliminary indications are that the masses are not high, that they are more consistent with the hypothesis of the rings being made of ices rather than something heavy containing a lot of iron.
On the planet itself, I think we've at least confirmed that these yellow bands are correlated with cloud heights. The various colored bands on Saturn are correlated with cloud heights, or by which I mean different colored bands are at different heights.
And then we come to this exquisite fine feature, the F-ring, a very narrow F-ring, which lies near or on the inside of the E-ring, which we have not been able to observe, but I have little doubt that the E-ring exists. And then this morning we heard then of the discovery of the G-ring between approximately 10 and 15 radii.
Now I know the ladies and gentlemen of the press are probably a little bit perplexed by some of the complicated figures that we show you, so I thought I'd start with a simple one. This is it. Now this is my summary of the hard information we had, hard scientific information we had about Saturn's magnetic field prior to the Pioneer 11 mission. So we know that we can now turn this blank page and begin to concentrate on the fact that Saturn does indeed have a magnetic field, and we know what its properties are. And to paraphrase William Gilbert, who started this business originally back in the 1600s, might say Saturn is indeed a giant magnet. What we've shown here is the Pioneer rock, which we presume lies in or near the ring plane. This is the Pioneer spacecraft, which at this time was about 10 minutes after having crossed the ring plane and was moving inward towards periapsis. It seems clear that referring to this as the Pioneer rock was perhaps somewhat misleading. As you've heard, the energetic particles have given us some idea about the size of this thing, which we nearly missed. And several hundred kilometers is probably more comparable in cross-section to the greater San Francisco-Oakland area. So calling it a rock is perhaps not really the appropriate thing. As far as we know, what wasn't there, we went under it about 10 minutes after crossing the ring plane, and I would say, along with the others, that we were damn lucky.
What this shows, we'll just keep it at this for the moment, is how, using trajectory information, we can learn things about the interior of the planet. First, we show here just a core, an inner core to Saturn, which will produce a nearly spherical gravitational field. It will be slightly flattened, and we show, again, very schematically, a trajectory flying through that gravitational field. Now we can add in a region of metallic hydrogen, and that can be shown by here. We add metallic hydrogen on top of the core. This will change the gravitational field, flatten it even more, and we'll get a slightly different trajectory as a result of that metallic hydrogen region. And then finally we show the outer envelope of Saturn, the liquid hydrogen region, and we show in a very exaggerated way the shape of the surface, or the geoid. We have a figure of the interior. This is built up by an inner core. I guess I have no control over how fast this accumulates, so we can let it go all the way out to the surface. But anyway, that inner core you see is made up of molten rock and iron. This model that we show here is essentially correct. It consists of about 3 Earth masses, but is of about the same size as the Earth. So we have a density of about 3 times what we have in the Earth, and a body of about the same size made up of rock and iron, but higher density by about a factor of 3 because it's inside of Saturn. Then we have an outer core where substances, water, methane, and ammonia have settled out of the upper regions of Saturn and formed a outer core consisting of about 9 Earth masses. And the boundary of that outer core is about 23% of the total planetary radius. Then on top of that is the metallic hydrogen region, which is consistent with the diagram that Ed Smith showed. And the boundary of that makes up about 58% of the radius. On top of that, a liquid hydrogen region. And then on the very top, a gaseous atmosphere, which we estimate to be about 300 kilometers deep.
Yeah, I just want to make a few closing remarks, and that is that, first of all, in the last 2 weeks, I think our knowledge on Saturn has increased by at least 1,000-fold, conservatively. And so I think, 2 weeks ago we didn't know very much about Saturn. I think we know a lot now. We got a lot of questions, and hopefully a lot of these will be answered as we analyze the data further. But I think we've learned an awful lot in the last 2 weeks compared to what we've known in the last 370 years or so.